To kind of recap, what we've done so far is, well, I imported this data set, the iris data set. And, prior to that, we talked a bit about the idea of qualifying the performance of your model on your data, right? Where we need some rigorous way to decide if our machine learning model is going to do what we expect it to do. And what we generally do is we separate our data, right? We have what we call cross-validation that includes a train-test split, where we split out the training data from the test data. And that's usually like a 70-30 split or an 80-20 split, or for some models, it's more like a 95-5 split. It really just depends on the problem and how much data you have. And as we saw before, the more data you have, obviously, the better, right? If the number of samples I have is 500, then, this little wavy model here isn't the worst thing in the world, even though it is following on the variation in the data more than we'd actually want it to. But that said, we started this kind of the workflow of machine learning, where the first step in general is importing, cleaning, and reshaping your data. We imported this data set, the iris data set, and the first thing, we took some quick peeks at things in it, right? Like, how many rows do we have? There's 150 rows. What are the unique classes that we're trying to predict? Setosa, versicolor, and virginica. And now I'm gonna go ahead and plot some data. This is universally a pretty good idea. If you can make some visualizations early on, those visualizations will call to light anomalies in your data, things that are broken. Often you won't be able to plot unless you actually clean your data. So it's kind of a diagnostic in real time on cleaning your data. Like, you might throw errors because you have some, null values in there, some not a number values, or some other kind of missing data. We don't have any missing data in this data set, thankfully. It turns out that's actually a very tricky thing to work with at different times. So what I'm going to do here is I'm going to plot. We've got these four columns, right? We've got these four features of our data, these four variables, however we want to say it: sepal length, sepal width, petal length, and petal width. And what I'm going to do is just plot each of these against each other and color code the class of the little point that I make. It's going to be one of three colors, and we're going to see which features in combination with each other best help to separate our classes out. And then we're going to do something a little counterintuitive, because this data is so kind of friendly. We're going to choose the worst pairings of class in terms of the worst pairing of features in terms of differentiability of the classes. And we're going to do that not because we would do that in the real world. We're going to do that because we want to make, we don't want to, how do I say this? Our algorithm will perform too well. We're going to get 100% accuracy unless we do that. And I just want to show that, if we can get less than 100% accuracy, there's some gradient of settings we can make to our model that will help optimize, even if we are using poorer features as opposed to better features. So let's see. I'm going to import something here that's going to help me with pre-processing. This is just kind of a binary encoder so that I can. You don't have to worry too much what that's going to do, but essentially it's going to take those labels, the target labels that we have for our classes, the versicolor, virginica, and setosa, and it's going to make them, put them in a better format for us to predict against, is essentially what's happening there. And then I'm just going to write a simple plotting function where I pass in this X data frame right here that I've called X. That's our, the features that we're going to use to predict some target. And then I'm going to pass in the target vector, which is Y. So notice big X for that, matrix, and little y for the vector of outcomes. And I'm also going to pass in, because we're going to pass in pairs of columns, so I'm going to pass in, the columns that we want to plot. So first thing, I'm just going to encode I'm going to encode our output vector through this little label encoder. Again, you don't have to worry too much about this. This is just kind of a utility in this case. And then we're going to look at every pair of features together. And if you think about it, this is every combination of features, not every permutation, every combination. So I'm going to do this in kind of a little bit of a brute force way because it's easier to explain as I do it. I'm going to make a list of tuples of the features. And so for column 1, in columns, and then I'm going to exclude one of them. And then for column 2 in columns, and then we don't want to plot any feature against itself, so we'll exclude column 1. If column 1 and column 2 are the same column, we don't want to compare them, right? So if those are the same, and if those are not the same, is what I mean to say. And this pairing, column 1, this tuple, column 1, column 2, if that's not already in our built pairs, if that's not in built pairs, and the other condition that we want to meet here is just the reverse of this, right? So I'm going to copy this whole thing. And again, this isn't the most efficient way to do this, but notice I'm just checking for these two arrangements, column 1, column 2, or column 2, column 1. And if I meet all of those requirements, then I can go ahead. I'm just going to do this explicitly. I'm going to say, well, then the tuple that we're going to add is going to be column 1, column 2. And also that's a pair. That's a unique pair of our features. So I can do this. I can just say built pairs.append that tuple. And now we should have every combination of built pairs. So for each of these, I want to plot them, right? And that's what I'm going to do. I'll go ahead and say, wait a minute. Yeah, okay. Just wanted to check my tabbing. So for pair in built pairs, the X label and the Y label, this is just the feature names. Now, the way that I can get this data out of X is pretty straightforward. I can just subset the data frame. And this is going to be the X label and Y label values. And that's just going to, dump these out to X. So now I've just got a smaller data frame to work with, and it's just going to be a little easier to read. So there's going to be min and max values, and I'm going to use these to define kind of the edges of my plot. I'm going to do this for both the X and Y, mins and maxes. So let's do this dot min, and then we want to give, I'm just going to give a little padding on the side, and then so that'll be our min value, and then this will be the max value. and a little bit of padding on the right side. And this is pretty much the same thing for the Y values, except now I'm going to use 1. This is the column 2, or the the second in the pair for each of the pairs. So comma 1.min minus 0.5, comma 1.max plus 0.5. Okay, that looks good. And then for each of these, I can go ahead and build the plot. And this part, I'm going to define kind of the area of the plot. And this is going to be a simple scatter plot. So we already saw this function a little bit earlier, plt.scatter. And I'm going to pass in the two features that are being plotted, which is these are the two columns in this matrix. And I'm just going to set a color for them, or set a set of colors, actually. And this edge color is just going to draw a little black circle around each plotted point. Okay. And then I just need to annotate these. So I'm going to annotate the X label, oops, and the Y label. Right, and I have these above, remember. X lab and Y lab are the names that I've gotten out of these pairs from built pair above. And then this is just cosmetic. Don't worry about it. And then this will, ultimately this will draw the plot, this plt.show. Okay, so all that's written. There's probably an error in there or something that I'll have to track down, but at this point we should be able to plot X against Y, and then every combination of features in X should be plotted against the color coding of the classes in Y. So let's see if that actually works. Okay, positional argument follows keyword argument. Does it? Oh, yes, it totally does. Because this is CMap gets this. CMap is just color map. Label encoder. Okay, there's no such thing as an encoder, so let me fix that. Okay. So we have plots, and let's go ahead do that. All right, so what's going on here? This is a plot that shows sepal width plotted against sepal length. And each of these colors, I don't know how clear those are. Hopefully they're fairly clear. We've got red, orange, and gray. And let me just draw something like a boundary between these, just just to get a sense of what's happening here. I see, like red is kind of all on that side, and then there's some kind of boundary here. It's kind of hard to figure out, actually. Something like that, where there's more gray over here and more orange over here, and then red here. So these, I'm just gonna say this right now, these are probably gonna be our weakest features in terms of determining the class. And part of that is going to be that these two classes don't really differentiate very easily. This class, whatever that is, it does differentiate very clearly, but yeah, I just want to make sure that we actually have a machine learning problem to train on. And if we look at these other ones, these other plots, like this is petal length against sepal length, these three classes we can kind of just draw a line between them, right? Like I could draw that line there, and then I could kind of draw a line roughly there. And we have almost perfect separability. So imagine if we trained an algorithm on all of these features, right? On all 4 features. Well, the combined effect of all of those features is going to give us a very powerful ability to classify into these 3 different classes. In fact, KNN, because of the nature of KNN, if you think about it, if we used these 2 features, I think it's likely that we might misclassify only this and maybe this one if we have a k of like 2 nearest neighbors or a k of 3 nearest neighbors or something like that. Everything else here is going to classify, and maybe this one. We might misclassify that one. Everything else here looks like it's going to be predicted in its actual class. So it's gonna, that's great in production and in the real world, but not so great if we're trying to show how to tune an algorithm. This one, again, we've got some really easy separability between these. I could separate those by drawing through them. As with this one and this one, and this is probably the nicest one, right? Like we could draw a line here and draw a line here, and we're done. So again, I'm using if I was trying to solve this problem in the real world, I would use optimal features. I'm not using optimal features here. I'm using the poorest performing features. And I'm doing that so that we can actually play around with the algorithm. Okay. Just I feel like I need to qualify that over and over again because what I'm doing here is a little weird. Okay. So after let's say we're done with our exploratory data analysis. We have some sense of our data. We've looked at it. We know how many rows we have. We know what our classes are. We've plotted things. We've gotten some initial, sense of how our features help define the class of flower that we're trying to predict. So the next thing that we might do is just train, test, split. And this is going to be pretty straightforward. I'm going to use, first I'm going to do a number of imports. So I'm going to import NumPy, which is our kind of massive linear algebra library. It's highly optimized. Under the hood, it's C and Fortran, and we use it to do a lot of stuff that Python can't do quickly. So I'm going to import NumPy, and I'm going to import a function for the train test split. So from sklearn model selection, I'm going to import train test split. And then I need to measure the results here, right? So I'm going to import from sklearn metrics. From sklearn metrics, I'm going to import just a simple accuracy score, right? So how many did I predict correctly out of all the predictions? That's all that's going to be. We could write that function, but it already exists. We might as well use it from sklearn. And then from sklearn neighbors, I'm going to import the kneighbor classifier. So notice that there's a kneighbor classifier. There's probably a kneighbor regression, right? If we were trying to predict continuous output values, as opposed to a class, right? A classification, right? We're predicting a class. So I'm going to import that classifier. And I'm just going to import one more machine learning model. And we're not going to do this here, but I want to just challenge you to go back through this code and try to plug in logistic regression everywhere where we use the k-neighbor classifier and run this again. And you'll have to change some code around to get it to work. But yeah, this is for you to try, to implement. Okay. And then now that we're here, oh, whoops. K-neighbor classifier. Oh, neighbors classifier. There we go. Oh, that's why. Okay. I'm trying to import logistic regression from sklearn neighbors, and it's a linear model. So there we go. All right. So I'm going to grab these least separable features that I described. That's sepal width and sepal length. And that's going to be our input x. So np.array, this is just going to build a data structure in NumPy that's called an array. Array is sort of like a multi-dimensional list, right? Like in this case, it's going to be a two-dimensional list. And I'm going to build it out of our sepal length and sepal width. And then I did this above, but I'm going to do it again. I'm going to just separate out our class. And then again, I'm casting this to essentially a vector. Although in NumPy, a vector and an array are stored in the same way. So I'm just casting this to an array. Okay, so we have x and y. And then I'm going to split them. And the way that these are split is very simple. I don't know why this is insisting on being there, but okay. But I'm going to go ahead and split into the train and test sets. All right. Oh, okay. It just, I don't know. VS Code has some strange behavior sometimes. So I'm getting xtrain and xtest. Okay. Again, I'm going to train the model on xtrain, and then I'm going to validate the model on xtest. And then I have ytrain and ytest. And this is just a simple function, train test split. I pass in x, I pass in y, and I decide what the test size is going to be. So the test size here is going to be 0.2. So I'm going to train on 80% of the data, test on 20% of it. And then I'm going to put in a random state. This is the same as the same idea as a random seed, right? So it's always going to split this in the same exact way. The reason I'm doing that is, when you're doing your first passes on trying to get something to work, it's just a really good idea to have your random be the same random for a while. Although when you get into actually trying to validate something, you're going to want to remove this random state, or you're going to want to try a bunch of different random states. Or as I mentioned before, there's this thing called k-fold cross-validation where you take out, different random chunks, 5 folds or 10 folds, and you use each of those as your validation. Okay, so now I've got xtrain and xtest. At this point, I'm going to search for hyperparameters. So what is a hyperparameter? A hyperparameter for us is going to be something we can change in our machine learning model. It's kind of like a setting in the machine learning model. And if we change that, it might improve its performance, or it might make its performance worse. And really, this is what we're trying to find when we do cross validation is we're trying to find good hyperparameters, good settings for our hyperparameters. So, offhand, what do you think is a setting that we can change in k nearest neighbors? Yeah, we can change k. Yeah. We can change the number of neighbors that get to vote on the class. So we pick a point, and maybe we look at 3 neighbors, or maybe we look at 5, or maybe we look at 10. And depending on how many neighbors we look at, it's going to change the majority vote. So this is a little bit of a harder conceptual question, but if we're what is more likely to overfit? And remember, by overfitting, one way we can think about overfitting is that we're connecting the dots, or we're following the signal, right? We're not following the signal, we're following the variation in the data, right? So if we're overfitting, and we don't want to overfit, right? If we're overfitting, we're going to be, looking at variation in the data, and that is going to be making the decision for us. And the underlying signal that, say, defines which class we're in is going to kind of be lost, or it's going to be obscured, right? Like when we look up here, if I plot something with degree 1, I know offhand that this is an order 1, or just a linear. This is a linear construct that plots these points, right? These are points that are offset from a single line, and then we've got this massive squiggly thing going through here. This is overfitting because it's following the noise. It's following the variation in our data. Whereas, so in this case, the fit complexity being too high, it allows for a lot of curvature in our plot. And, this is linear here, right? This is linear. If I change the fit complexity to 1, well, we get a decent fit. And I think even with a fit complexity of 2, we still get a decent fit. Although we do get some curvature in there that's unnecessary, it's not doing a terrible job. Now, that's for a linear model. What do you think? What do you think is more likely to overfit in this in this k nearest neighbors model? Remember, our neighbors are voting on us. What do you think is more likely to overfit? A high value of k or a low value of k? And why do you think that? Yeah, okay, so a low value of k. Why do you think a low value of k would be more likely to overfit? Yeah, totally. It puts too much weight on one vote with nothing to argue against that vote. Yeah, and I like to think about this as, okay, well, I'm just going to go ask my next door neighbors if I'm a good person. And I'm only going to ask the person next door. And it's really just up to them to decide if I'm a good person or not. Whereas if I'm really trying to be fair to myself, maybe I'm going to ask a huge cross section of random people, let them get to know me, right, and then have them decide. But maybe my neighbor just hates me for some arbitrary reason, and I don't know. They're just going to vote poorly against me. And if we allow that, and there are times where a very low value of k could be good, but as we'll see, a low value of k in this case is actually going to perform pretty poorly. So, yeah, I'm going to search for optimal hyperparameters, and part of doing this, this is really where we build our model, right? This is where we build our model, and we fit our model, or we train the model on the data, and then then we get something out of this at the end that we plot. And this doesn't mean we have something ready for production necessarily, but this is almost there. And in this machine learning workflow, a lot of the time, what you do is you get to step 3, and then you go back to step 1, and you do 2 and 3 again, and then back to 1 and 2 and 3 again, and you keep doing this over and over and over again, because at the end of the day, you're looking for optimal hyperparameters for your problem, right? And once you have those, you can train a model on new data. You can, figure out a whole bunch of different ways to build models and lightly adjust your hyperparameters as you go. But we're going to try to cast a fairly wide net. And we're going to optimize for accuracy score. So I'm going to make parallel lists here. I don't need to make this a list. I could just keep it as a range. But we're going to think about neighbors between 1 and 99. Right? So 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors, all the way up to 99 neighbors. And then I'm going to get accuracy scores. And CV here just stands for CrossVal. So I'm going to get accuracy scores for the train set. So mind you, what's happening here is I instantiate the KNN model. I fit the KNN model on X train and Y train. I pass in X train and look at Y train predict, like what do I predict on those training values. And then I pass in X test and then look at Y test predict, right? Compare that to the actual expected Y values. And, at the end of this, I'm going to have a kind of a set of accuracy scores for both predictions on the training data and predictions on the test data. So for CV train scores and CV test scores. Now, which one of those, of the training scores and the data scores, which one of those is more important for deciding what value of K to build in my production model? Any thought about that? Remember, we're training the model on X train, and then we're getting accuracy scores on predictions on X train and predictions on X test. So we're getting scores for both of those. Which is more important for deciding the best value of K? X train or X test? Or sorry, our train scores or our test scores? So let's see. There's a vote here for train scores. Let's go ahead and code through this, and I think it might become a little more apparent. So for each value of K in neighbors, so we're going to instantiate a KNN model, right? With so K neighbors, there it is. We're going to instantiate this with the number of neighbors equaling K. And then I'm just going to fit the model on the data, right? This is where we do that. KNN.fit. We pass in X train, and we pass in Y train, which are the corresponding target outcomes. So at that point, at that stage, we have a working KNN model, but we don't have an understanding of the predictions quite yet. So let's get the predictions on train, and there's going to be I'm just going to make this thing called yTrainPredict. knn.predict. I'm going to predict against... Oh, yeah, I'm going to compare this, the training scores. Sorry, I'm kind of misspeaking here. I'm going to compare yTrainPredict against yTrain actual, right? yTrain. So that accuracy score is just going to be the comparison between yTrain and yTrainPredict. So I can do that with our training data, and then I can just change all of these to test and get the same stuff on. I can get all our predictions on the test data as well. So let's pass in x test, and then this is going to be CV test scores and y test against y test predict. Okay. So hopefully. So notice that was pretty quick. We just ran this we ran this 99 times, right? And it's a, to be fair, it's a very small set of data. It's 150 rows of data. But this is partially the power of NumPy. NumPy is able to just use massive matrix operations to solve a lot of these problems. It kind of takes a matrix as a mask and superimposes it on other matrices in order to perform computations, as opposed to what we do with lists, where we we iterate through them. We look at each value and we do perform some kind of computation on it. So that was really fast, for 99 iterations of 150, like the processing 150 rows of data. Just wanted to point that out. Okay, so let's look at what does this CV train scores look like. So these are all going to be between 0 and 100%. Notice this is for k equals 1, right? When k equals 1, we have 94% accuracy on our training set. And then notice we have some kind of steady decline here. Well, it holds pretty steady. It doesn't go below 70%. Starts off at around 94%. And then if we look at our CV test scores, notice we're increasing up to a point. We have 90% there, 86%. That this 90% might be our optimal value of k. So what is that? 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe that's k of 12 neighbors. Maybe that's what our optimal is. Okay, so let's look at this. Let's plot these results. That's often what you want to do with something like this. And I'll try to talk through this in a way that isn't too inundating. So let's see. So I'm looking for the optimal accuracy, right? Which is going to be the highest accuracy in CV test, right? So our test max is going to be at the index of the maximum value from CV test scores. And then we have an optimal k value that is just neighbors sub test max. So what is our optimal k? Let's find out. Looks like it's 12, which means I counted correctly. And yeah, I'll just start plotting this. I'm going to set an X limit on our plot, which is going to be at the end of our neighbors, right? So we want to plot that whole length, right? 0 to 99. And axes dot set. We're going to plot a Y limit as well, which is going to be sorry, it's going to be lightly constrained. It's going to be from the minimum of our test scores minus 0.2. So that gives us a little bit of range below the min test score. And I'm going to color code these just so that they're, you know, slightly more readable. We'll do orange and blue for train and test respectively. And that's what this mpatches thing is that I imported. So let me just set these, color orange. And I'll give it a label. And that'll make it nice because we can have a key to look at these. So we have an orange patch, we have a blue patch. And plt.legend, and now we'll just have a legend in here, and orange patch, blue patch, and that should be about it. You know what? Let me put a title in here really quick. So accuracy CrossVal, and we have some optimal value of optimal K. And now we can just plot both of these. So I'll plot the test scores. And put that label, test scores, and we'll plot the train scores. Okay. So set ylem. Where is that? Small typo. Okay. So here we have a plot of our scores. And how can we read this? Well, first let me check. Okay. So, how do we read something like this? We're in general looking for some best value of K. And we can see, we know that it's 12. We know that that's our best value. And we can see it right there, right? Blue is our test. And that's really what we're trying for. Now, keep in mind that we set a random seed here. So if I go and change that random seed, it's very possible, and I'm just going to say it's probable, that we're going to have a different optimal K. So why don't I run this again with a different random state. So it's at 15. Let me set it to 45, and let's try this again. Now our optimal K is 29. Okay, right? So this kind of, this brings up some other issue here. What is the best, what is going to be our best K to choose on data we've never seen before? And how do we go about figuring that out? right? 33. Well, are we going to decide it's 12 or 29 or 33? I mean, if we're being critical about this, we're not going to choose any of those, just because we like one of them better than the others. What we're going to probably do is run this a whole bunch of times with different random states, and then maybe average the results of k. That's one thing we might do. In fact, that's probably what I would do in this case. Or really what I think would be the best thing is to get more data. We're dealing with 150 rows of data. We're going to see very high variability out of this because we're sampling from 150 rows. And so this is going to be somewhat of this optimal k is going to be somewhat of a moving target. But we can constrain that. Maybe the best way to constrain it would really be to, if we can't get more data, to just run this a bunch of times with different random states and, average those values of k. And what we would get out of that would hopefully be our most generalizable model. Okay, so what do we do from here? This is, we're not exactly done here, but this is where most of the work has already been done. I think at this stage, let's say we figured out an optimal k, and let's say that it did happen to be 33. Well, that's a really good question, and let me stop myself before we go forward. And the question is, when you look at the train versus test graph data, where do you want to see the lines in comparison of each other? I'm going to say something a little, something that's not totally true, and I could say that we don't even need the training line in here. We don't really need it. That's a true statement, but we do want it. And part of that, for me, is like, okay, well, where are we overfitting? Where are we underfitting? Now, obviously, our results for our train are really good here, right? The results for train are really good right here. And I think that shows us where we're overfitting, right? We're overfitting when we have a value of 1 or 2. And I think what we can also see is that out here, we've got this trend downward, right? We've got a trend downward, which says to me that we are likely underfitting over here. I didn't really talk about this, but what happens when you have 150 rows of data and you're voting with all 150 neighbors? Well, you're trying to be too general at that point, and there's some balance that you need. Because at the point out here, you have really, really different. You have really different values. You have really different neighbors that are voting on you, and you don't know them. They're just voting on you. So when we get out here, we're starting to underfit, and I think this is the value of having these two lines. Where we want them in relation to each other is harder to answer. I think it's more that we're getting a sense of the performance of our algorithm on the data. And I think this is kind of cool because, there's a certain point, some threshold that we cross here. If we were imagining that this was with a bunch more data and we could count on this being the, a good result, this 33 for our optimal K. At some point, we cross some boundary and we're like, oh, from here until here, we're doing pretty good, right? We're doing somewhere around 84, 85. And, then we have a peak here. So, we're even doing good on our training data. We're good in comparison to what we're doing out here or out here, right? Somewhere in here, we're doing the best. And I think this might tell us, at least with this algorithm, that maybe we would want to choose something higher than 33 because we would want something more generalizable. Something more along the lines of 42 could be. Or maybe we want to take something right in the middle, maybe. But I think that's what we want to see. What we're looking for is how it performs on the training data, how it performs on the test data. Because if let's say it performs, you train a model on some training data, and then you look at the scores on its own training data. If it does really poorly, that might be an indication that the algorithm itself is not the best algorithm to use for this. Like maybe that data doesn't play well with that algorithm, or maybe you don't have data that's good for making predictions. Maybe there isn't a clear enough signal in there, right? So it's not necessarily how they compare to each other so much as what we can start inferring from this, how we can interpret it. But at the end of the day, we're really looking for some optimal value for a hyperparameter. In this case, it's somewhere in here, could be 33. If we move around our random seed, it's going to change what k is, and we can find more sophisticated ways to get an optimal value of k. Okay, so the next thing we can do is, let's say we have figured everything out and we feel fairly confident in our results. We're going to fit our model for the last time and go from there. So this is just going to be as simple as what we did before, where I say k neighbors classifier. I pass in as the number of neighbors our optimal value of k, and I fit this model on X train and Y train. And our model is built at that point. And then we get our final metrics that we're going to report, and say, okay, this model that we're taking into production, it performs at this level, essentially. So we're going to do our model predict, and this will be, simply from before, ytrain predict is going to get knn.predict on xtrain, and then we've got also ytest predict for x test. And finally, this is where we report our metrics. And I'll just make a, we're only considering accuracy here. We're not considering any other kind of score. Make sure that you round these things, right? What does it mean? What does the 15th place of your accuracy score mean? Nothing. Nothing doesn't mean anything. So, just make sure you round these appropriately. And, I'm going to go for 3 here. I think 3 or 4 decimal places is generally pretty good. Oh, whoops. So this looks like, we made a model that can predict with 86.7% accuracy the class of one of these 3 irises based on the sepal length versus sepal width. And yeah, so the last thing to kind of think about this is, try swapping in logistic regression or some other model for KNN. And you might have to tweak a couple things, but you probably won't have to change very much. What I would do after that is try swapping in a different data set. You'll probably have to do a lot more editing of the code that's there in order to accommodate a different data set. But there are a number of toy data sets that are clean in the way that, the iris data set is clean. So, this is a general framework. And with a general framework, you can do a ton of different things. Keep in mind, all data is different, and these models are all different, very different from each other. Also, there's this idea of no free lunch, where there's no one model that's going to do everything on every data set. That's just how it is. Different models will perform better on different data sets, and it does take some trial and error and study. One of the things that we do all the time is we consider the problem that we solved or that we're trying to solve, and we look for other people who have solved similar problems with similar data. We look at how they did it, and that is a good practice. That's not plagiarism or anything like that. That is a good practice because there is a massive world of data science, right? So let me just show you this. I don't know if this will be daunting or inspiring, but so this is Archive, and I don't know how many of you have spent time on Archive. So this is just a huge database of published work, right? And a lot of this, let me see. Let me look up. I'm just gonna Google what fee. Let me think of something good. I'll do infrared pedestrian detection. How about Fusion Network and archive.org. Okay. So here's a paper. Anchor-free, small-scale, multispectral pedestrian detection. This is, there's code and related papers, and we can view the PDF offhand, right? This is all openly published. So I can go and look at this if I'm trying to solve, let's say, a thermal detection problem in light of pedestrians for some self-driving car, maybe some emergency procedure in a self-driving car. If there's thermal that pops into kind of a safety camera or something like that. This I'm like, well, how do I do this? Well, the first thing I do is I probably am gonna go start reading papers. And there are hundreds and hundreds of papers published every day here, just so you know. So, yeah, there's a ton. There's a world of information. A lot of people have already solved problems that look like the problems that you're going to try to solve, but they haven't solved the problem that you're going to try to solve, right? And so you're going to go out there and you're going to see what they did. And it'll inform how you go about solving the problem that you're looking at. Anyway, Archive is amazing. It's an amazing resource. And, this question, is this a database of scholarly journals only pertaining to coding? No. It's pretty diverse here, actually. Like, they've got a whole section for quantitative finance. quantitative biology, computer science. A lot of if I look in here, machine learning is falling under computer science here. It's also falling under statistics. And if I look at recent under statistics, it looks like today there were 92 things published here on statistics. I think that's how I'm interpreting that. I think that's either they were published today or they were put up here today. Either way, pretty amazing though that this is here. I've spent a ton of time looking through this. Okay, let's take a 5-minute break, and when we get back, we'll jump into kind of a series of challenges. I'll just pose challenges that look like the technical interview. I'll spend a few minutes talking about the technical interview, but then we'll just do a bunch of coding, really. Okay, see y'all back here in a minute. All right, I'm just grabbing some formulas that might come in handy. So just be 1 sec on that. All right. So I'm gonna kind of just come up with some prompts, and we'll treat them like challenges, and that's how we'll go forward with this. So the first thing, just kind of want to talk about, you know, what we expect you to be able to do, and kind of how to think about the technical interview. So, just in brief, like you'll have 45 minutes to solve a set of problems in a Jupyter notebook, right? So you'll use TeamViewer to connect to this remote instance of a Linux machine, and you'll go end to end on this Jupyter notebook. And you don't necessarily have to get everything done. You don't necessarily have to get everything right. What we're looking for is your ability to code, right? To code mathematical concepts, to answer some basic statistical questions, and essentially use your critical approach. What I've been calling a general analytic approach. We can think about that in a variety of ways, right? If we create our own phenomenon that we analyze, or if we analyze an existing phenomenon, like some kind of Poisson problem, for instance, or a binomial problem. Some of the things that you'll want to be able to do, you want to be able to recognize and solve a binomial problem, or a Poisson problem, or a geometric problem, or a uniform distribution problem, or a Bayes theorem problem, or or more basic probability problems, right? Like problems that of independent events using the multiplication rule. You want to be able to solve those kinds of problems as well. You're going to want to be able to translate some fairly simple, but translate mathematical formulas into code. That's something we expect. Like any of these formulas I have over here, we'd expect you to be able to code that up right away. And even at times things somewhat more complex than that, right? Something with a summation. Whenever you see a summation, there's a good chance you're going to be writing a for loop. If you think about writing a CDF function for Poisson, the CDF for Poisson is the summation of Poisson for varying for k from 0 up to n. And that's, we'd expect you to be able to implement that upon seeing the formula itself, So you see the big sigma symbol. Oh, I thought I had sorry, 1 second. We might actually need just a quick drawing pad here and there. Yeah, so if you see, right, something like this, so it turns out that my tablet has a defect. I'm gonna have to send it back, but it actually starts drawing before I start drawing. Oh, wow. Okay. So hopefully this won't be too terrible. Okay. Imagine that says I equals 0 and not something, whatever that says, up to n, right? We could plug in the Poisson. Okay. Let's just pretend here that this is even okay. Poisson for a lambda and I, right? Let's imagine that's actually readable in some way. It's the summation of the results of Poisson, right, for some fixed lambda up to I. Now, what if we had a fixed k value and we varied lambda, right? That's another possibility. that's something that wouldn't be that shouldn't be too surprising, right? And then you take those results and pack them into a dictionary where the key is the value of lambda, and the value is the probability of that lambda and k events. Okay, so I'm not going to do that again. I'm not going to try to draw with this thing anymore. It's I thought it would still be slightly okay, but it's not. Okay. So the kind of the heart of all of it, though, is this analysis through dictionaries, where you pack values into a dictionary and, making sure, well, there are times where you need to check membership, right? If you're going to increment, if you're going to increment a value in a dictionary, you need to check and make sure that that key value pair is there already. If you aren't checking membership, if you're just assigning, well, then you can assign the key with a value, right? Like when we packed in a dictionary with the Poisson PMF. Yeah, and then, kind of this general analytic approach that we've applied a bunch of times, where we create a process, some generative process, some data that we're looking at. We pack it into a dictionary and look at it, and then we interpret it. Okay. So let's think about some problems here, and I'll paste them into here. How about this? We'll start with just some. We'll just start with a problem. Okay, so you're sitting on a dock watching boats go by. On average, 2 out of every 13 boats that goes by has shipping containers on it. What is the probability that in one particular set of observations, 10 out of 20 boats have shipping containers on them? So that's the problem. I'm gonna put 4 minutes on this. You might need to code something to solve this. You might need to implement one of these functions on the right to see how it goes. Okay, so to start answering this question, first thing you need to figure out is what kind of question is it, right? To me, well, we're looking at some kind of binary outcome, right? Either, okay, we're sitting on a dock, 2 out of every 13 boats that goes by as shipping containers. So a boat either does or does not have a shipping container. That's a true or false. So that's going to say to me, well, maybe this is binomial. Maybe it's geometric. Maybe it's Bernoulli. But this should give it away. What is the probability that 10 out of 20 boats have shipping containers? So that would say, to me, that says our n is 20, our k is 10, and our probability here is actually, 2 out of 13 has shipping containers. So I'm going to say 2/13, and then I need to throw this into the binomial PMF, nk and kp. Okay, well, we don't actually have a binomial PMF defined yet, so I'm going to have to define that. So what I'm going to do is I'll do from math import factorial, and well, if I'm using binomial, well, we have a combinations function in there, right? So let me just define that really quick. So define coms, and that'll be n and k. So that's our n choose k, and we can just return factorial of n over factorial of n minus k multiplied by factorial of k, right? And then we can look at the binomial PMF. And mind you, on our interviews, we'll always provide formulas, so you don't need to memorize these formulas. So binomial PMF, and then this is n, k, and p, and this is just coding. This is going to be coms of n and k multiplied by p to the k multiplied by 1 minus p to the n minus k. And we just return all of that. So, let's try that. Let's see if that works. Looks really unlikely. 0.002582, and that's okay. This looks right. Coms n choose k, p to the k, 1 minus p to the n minus k. Yeah. So that looks very unlikely, right? That we're going to see exactly 10 out of 20 boats with shipping containers on them. Okay. So this is part of it. Discerning, if we're using a distribution, if some distribution that we've studied, or if we're looking at some kind of other random process. And let's do another one that is from our known distributions, our known probability approaches, and then we'll do something that's a little bit less, a little bit striking out and exploratory. So let's say two black cars go past the stop sign every 15 minutes. What is the probability that more than 10 cars pass the stop sign in 1 hour? And again, let's do 4 minutes on this. Okay, I'm gonna put 2 more minutes on for this, and yeah, just we'll see where people get with it. Okay, so apologies if I stumped anybody on this one. So this is a Poisson problem, right? Now, we have some value of lambda. Lambda for us is going to be 2 cars every 15 minutes. And then we're transforming it by 1 hour, right? So it's going to be 2 times 4, so our lambda is 8. We would expect 8 cars in 1 hour. What is our value of k? Well, the first thing to consider is that we're thinking about more than 10 black cars. We're thinking about more than 10. So not only do we need a Poisson PMF, right? So we need Poisson PMF. We're going to need the CDF as well. So Poisson PMF, lambda, k, and then we can just return e to the negative lambda multiplied by lambda to the k divided by factorial of k. We'll need e as well. So some from math import e. I'll just put this up here. Okay. Now we need the Poisson CDF. And this will be lambda and k. And then we'll make an accumulator, simple accumulator. And we'll go for k in range. I'll change this to k high just to in range from 0 to k high plus 1. Our accumulator is going to get our accumulator is going to be incremented by the Poisson PMF with lambda and k. So once we do this, we can call the Poisson CDF on lambda and k high. Now, what is k high? K high is going to be 10, but this is going to get us the probability of between 0 and 10 cars, right? So we actually want to, we're thinking about more than 10 cars, not 10 or more, but more than 10 cars. So we want to get everything off to the right of that. So that's going to be the complement of this, which is going to be just 1 minus the Poisson CDF. Okay, where's that? 68. 1 minus Poisson CDF. Because I'm not returning anything. That's why. Okay, it looks like the result of that is 0.184. That's the probability that more than 10 cars will pass by in an hour. So these are examples of implementing, mathematical, just functions that we provide you, and then, looking at that outcome. Now, let's do something different. This is more a kind of random variable problem. So I'm going to define a random variable. And let's say A is the result of, of rolling a 4-sided die 5 times and processing it through this function. So maybe it makes sense. Let me just write this function out really quick in the slides. All right. Just going to write this in LaTeX. This is going to be the sum from I equals 1 to to 5 of roll sub I. What's going to be text roll sub I multiplied by 4 over I. Okay. So process through this function. Let's get back over to here. So the random variable A is the result of processing through that function. And I'll put a little more context to this. So I'll give an example. We're rolling a 4-sided die 5 times. What are the values available in a 4-sided die? So a single roll has potential values 1, 2, 3, 4, right? So we're thinking 5 rolls from this. So an example set of rolls is going to be, well, I don't know. It could be, 1, 3, 1, 2, 5, right? 4, not 5. How would we process this roll? Well, we would say the first roll would be 1 times 4 over 1. Then we add to that 3 times 4 over 2. 1 times 4 over 3. 2 times 4 over 4. And then 5 times 4 over 5. And that would be some random roll of A. Okay? So you're going to write a function. You're going to write a couple functions here. The first is going to be, well, you need to get a roll, right? So think about how to do that. Get four-sided roll, and the next function would be this math, which I'm just going to call roll math. Okay. So you're going to pass in that list and then write something for that. Okay. So I think you have everything you need there. Let's do 6 minutes for this, and yeah, you're gonna write these two functions. I'll pass these stubs in to Slack. And I'll set a 6-minute timer. Okay, so let's go through some kind of solution for this. Now, you could have written this in a couple of different ways, and I'm going to be a little opinionated about how I write it, and I'll just start going through it. So we're going to need random choice, right? So from random, import choice. And this first one, this get four-sided dice roll, or four-sided roll, I can just return the choice from 1, 2, 3, 4, right? Now, this roll math, I put in a parameter here, list. Now, we could pass in a list of 5 rolls, right? We could do that. We could hard code that this will always do 5 rolls, and we could just make 5 calls to four-sided roll. I'm going to assume that we're going to build a roll. Let's say roll 1 is going to get, I'll do a comprehension here. I'm going to get a four-sided roll. I'm going to do that, however many times. Let's do that 5 times, right? Do this for let's see, for you know what? I am going to just do this as this is a good chance for comprehension, but I'll do it explicitly just to not confuse anybody. But for whatever in range, and I'll do this 5 times. Roll 1 is going to have appended to it a four-sided roll. And then at this point, we should be able to call roll math on roll 1. Now we need to, since we're passing that in, now we need to fill in the logic here, right? So I'm going to say, let's just make it an accumulator, and and we'll say for IDX and val in enumerate the list. And notice we're starting with an index of 1 here. I is 1 when we start. So, and if I was 0, right, we would throw an error because we can't divide by 0. So let's do that. And this first value, roll sub I, is going to be multiplied by 4 over the index. So that's what we increment our accumulator by. We return the accumulator, and let's see what that is. So it looks like that on a random roll, that's 17.47, right? 22.93, 26, 20, 29, 19, right? I can keep running this. It would be better if we packed these values into a dictionary somehow. So that kind of gets us to the next stage. We've defined a random process. Now we want to kind of analyze it, right? So let's think about how to do that. Now, think about these outcomes. Think about these outcomes. What is the maximum number of outcomes that we can get out of this? How many different values for A can we have at the most? It's a base 4 system. And we've got 5 places in base 4. Yeah. So it's going to be 4 to the 5th power. So let's pack this into a dictionary. We don't have a whole lot of time. Otherwise, I would challenge you to do this. But let's think about this in terms of analysis, right? So I'm going to kind of flippantly, because I haven't done this before, I'm going to code it procedurally, and then I'll pack it into a dictionary after I do that. So let's, you know what? I'll just start writing a function. So let's analyze these outcomes. And we're doing this for, you know, the number of places is 5, and let's do this for some number of samples. Let's do 10,000. I think that should work. And let's do that. We'll make a dictionary. And then, so this is our classic sampling pattern for whatever in range num samples, right? We don't need this value. We don't need to know which sample it is. The roll result is going to get, it's going to get something like this. So how about I do this? Get roll of 5, and I'll just return roll 1. Okay, so now that we're doing that, I can get the result of that, and then I can get the roll math, right? So roll math, I can call that on the roll result. And I'm going to go ahead and round this to 2 places. And I'm doing that because I'm looking at this and I really think that we're getting repeating digits after a certain point, right? And it's really these first, the, you know, tens place through the hundredths place that are meaningful. So I'm just going to round that to 2 places. And that's going to be our result. Okay. So at this point, I can say, well, if that result is not in the dictionary, then I can append it, right? So d sub res is going to, not append it, I can put it in the dictionary. And I'm making a counts dictionary just to start with. And now I can increment this by 1. Okay, so let's return that dictionary and traverse it and see what kind of thing we get out of this. So I'm going to say for outcome and value in the sorted version of, what am I calling this? Analyze outcomes. I'll just call it d.items, or I'll call it d and call .items on it. We'll just print. Again, this is one of those patterns that we kind of harp on, but just printing the f string, where we print the outcome, right? That's the value of a, and we look at the count of that outcome. Oh, you know what? I don't know why I did it like that. Let's do outcome and count. So let's see if that doesn't have a bunch of errors in it. Oh, no, it doesn't. That's cool. So I'm looking at this and Offhand, you know what? I don't think we need to have quite this level of granularity. And I'm going to drop 2 of those decimal places. And at that point, at the point where I drop these decimal places, we are no longer looking at the individual values or representations of the individual values. We're looking at bins, like whole number bins, right? So why don't we look at it in terms of whole number bins? And we have a fairly interpretable distribution here. So let me grab the top part of this distribution up to 608, and grab the bottom part of the distribution. Okay. So at this point, we can start thinking about this and interpreting it. One of the questions offhand is, well, where, what is our more common value for A, for our outcome? It looks like it could be 22, it could be 24. Is it possible that we have a bimodal distribution? Well, the way we might, kind of qualify this is, let's run it again. 20 is 606. Okay, well, maybe that was just in terms of variability, right? This time, we're looking at some sort of fairly even spread between 19 and 25. And maybe we would want to qualify this, right? Here, 23 is standing out. 24 is standing out. So at this point, we want to start asking questions and interpreting what's happening here. We can take that back to the math, or we can try to describe it in terms of what we're seeing. Now, there's another way we could do this. We just used a sampling approach. What else could we do here? What would be maybe more exhaustive? If we wanted a fixed value of counts, if we wanted to know what the theoretical probabilities are here, what would be better? So it may not be obvious looking at this. We took a sampling approach, right? We're sampling here. Choice from 1, 2, 3, 4. This would not be so computationally unfeasible. We could nest some for loops and take a counting approach, right? And then we could pack those into a dictionary and look at the outcomes. We could call roll math on that and look at those outcomes and get a very definitive, because I think what we're going to find if we bin these, we can ask a question like, well, what is the probability of getting a value, that rounds to 26 or that falls into the bin to 26? If we wanted to truly bin it, we probably wouldn't round. We'd probably floor. We'd probably just cast this to an integer or something. But the point being, we have some kind of phenomenon that we can explore. We can ask questions, and we can try to start figuring out, well, why is this, this approach to this random variable, why does this get us this distribution over here? And, we can explore that deeply, but at this stage, we can answer questions like, what is the probability that you get a value less than 24, right? We can answer that question at this point. So our interviews look kind of like this. And I think this is a little more obtuse than our interviews might be, because we're kind of inventing a new phenomenon that's a little bit, this is a little bit harder, maybe. But the expectation that you code functions within a short amount of time is there. And the expectation that you recognize a binomial problem or a Poisson problem, that expectation is written into the interview. Basic stats understanding, right? Like considering things in terms of the average, looking for centrality, and also looking for a pattern in the thing that's been created. Okay, so let's stop here. I guess we're 2 minutes over. Thanks for being patient or sticking in. The next steps for, you have to qualify this yourself. What I'm going to suggest everyone do is reach out to Remy Arata, or reach out to me to set up either mentoring or a mock interview. And what we'll do is we'll take you through, we'll qualify where you might be struggling. There's a fair number of you who might not think you're ready for the interview, and you probably are. I'm sorry if I scared you at all with this, but you probably are ready for the interview if you've been able to, get maybe 60% of the challenges in throughout the course, right? Within the time constraints that we provide. That's something that, you can meet up with one of us. And I know that kind of takes the edge off if we run you through, kind of a barrage of problems and we say, okay, well, this is what you can work on. Or we'll say, you can work on this. You also seem like you're ready. And it's better to interview a little bit sooner. Also, because we can point you at next step materials, right? You've been in, Python and basic stats land. We can move you into the machine learning world pretty quickly and get you really primed for the DSI. So the sooner you interview, the better in that sense as well. Okay, I'm gonna go ahead and spin down, or I'm gonna stop recording, and I'm gonna stay on for 10 minutes or so, and feel free to ask me any questions. If you want to defer to the next class, send me a quick message and I will get you deferred, and that's gonna start on Monday.